So hello everyone. Today in this video we are going to see how can we design and verify our RAM module. So before starting the design part, let me discuss you some few important points which you can understand before starting your RAM implementation. So let's start this. So suppose this is our RAM memory. So RAM stand for random access memory. Like your RAM memory is volatile. What does it mean? So whenever you are doing a power off or something, so it will lose their memory or lose their data inside it. So the RAM has some following signal. Let me list down all the signal. So RAM firstly it have clock, and then it also have reset signal, and along with that it also has write enable signal. So I will discuss more in detail about all the signals. So after that we have address signal, and then we have write data signal, and then at output side we are getting read data. So see how it is working. So suppose we have 16 cross 8 RAM. So let's see the working of this RAM. Now let's discuss on all the signal. So first of all you have one clock signal. So your entire memory is synchronized with this clock signal. Like whenever you are getting some active edge of clock, then at that time only you are doing certain operation on the RAM. Then we have one reset signal. So your reset signal is basically resetting your RAM. Like whenever you are applying reset signal on your RAM, so it will just make your all memory location to 0. So that's how your reset signal will work. And then after that we have write enable signal. So see, when your write enable signal is 1, that means we are writing some data inside the RAM memory. Let me again repeat. If you have write enable signal as 1, what it means? So see, whenever your write enable signal is 1, that means we are writing some data inside the RAM. And whenever we have write enable signal as 0, so that means we are reading data from the memory location. Okay. So here we are reading data from the memory location. And along with that you can see and you can also see that like we have considered 16 cross 8 RAM memory. So what does it mean? So it means the RAM has a depth of 16. So here 0 to 15, it will goes up to 0 to 15. And in each block in each block, and you can say that in each memory location it will have 8 bit of data. So that how we can say that like 16 cross 8 RAM will be formed. Now let me discuss you the RTL implementation, and then we will check the verification plan of RAM using Verilog only. So let me take you to the code. So let me take you to the EDA playground. So let's start making RTL code of RAM. So first of all we will try to make our RAM code more generic, so it will be helpful for all other memory also. So we are considering 16 cross 8 RAM. What does it mean? We have 16 depth of memory, and in each memory location we are storing 8 bit of data. Let me first declare module. So module, and module name was RAM memory. So let's write it down, RAM memory, and let's declare all the signals or port, you can say. So first of all we have clock signals, and then reset signal, and then write enable signal, address signal, and then write data signal, and then read data signal. So these are all the signals which we have with the RAM. And let's declare the port. So input port, so our clock, reset, and write enable is of single bit input port. And then let's declare one parameter so that it can be easy for us to override it whenever we need some other kind of RAM memory. So let's declare one parameter, and parameter like address bit. So here we are considering 4 as an address bit, because see 2 raised to 4 16. So whenever you are considering 4 bit of address bit, so it will go from 0 to 15. So that's how you can consider it. Now let's consider the data bit parameter, data width. So our data width is of 8 bit. See, we have considered 16 cross 8 RAM. So that means we have total 16 memory location, and at each memory location we have total of 8 bit. And let also consider the depth. So our depth was 16. So we can simply write it 16. Now let's consider the address port. So sorry, this is a Verilog, so we can't use logic. So input wire, and now our address width. So address width -1 down to 0, and this signal is address signal, and so this signal is address signal. So this is how we can represent it. Now another signal was data bit. So data bit, and now this signal was our write data. So write data was an input port only. So we have declared it in an input port, and the name of the signal was write data. So we are writing data, and then similar like that we have output signal which is read data. So the output signal will be declared as reg type because we have to store something. So that's why we are declaring it as a reg type. And here the bits of the data will remain same as compared to write data. So this it will be the same as write data. And let declare read data, and let declare it's like read data. Okay. So we have declared all the ports. Now let declare a memory storage, and our memory will be of 8 bit. So our memory will contain data which is of 8 bits. So just write this parameter name data bits -1, data bits -1 down to 0. And suppose we are considering RAM memory. So let's note down the name RAM memory, and then the memory location, which means depth. So our depth was 16. So let's suppose we are considering depth -1, and so let's say we are considering 0 to depth -1. So first of all we have location of 0, 1 and so on, and it will goes up to 15 only. So that's how we can declare our all the ports and memory. Now let's try to make the logic. So always at the rate pauses of clock. So we are considering the positive edge of clock. So what does it mean? So whenever pauses of clock will arise, then this block will be triggered. Okay. So whenever rising edge of clock or pauses of clock will arise, then this always block will be triggered. So let's declare begin end and then end module. Then end module. And then inside that, if we are see as this design is synchronous, so we are taking reset inside the always block. So if the signal is reset, so if reset signal is high, so we have to make all our memory address to. So if reset is high, so we have to make all our memory location to 0. So let's consider a for loop, and integer I is equal to 0, I less than, we have to go up to depth -1. So depth -1 and I plus plus, and we have declared I plus plus. Now we have to make our memory location 0. So what was the memory? No. So here, so see here our memory name was like RAM memory. So we are writing it down RAM memory, and we have to make it 0. So since our memory location is of 8 bit, so since our each location consists of, since each location consists of 8 bit, so we have to declare it all the location to 0. So that's how we can able to achieve our requirement. Now if reset, so we are making our memory or allocating 0 to each location of our memory, and then else if write enable signal is high, so we are writing some data, which means we are writing some data inside the memory location. So begin end. So if our write enable signal is high, what does it mean? So we are writing some data in the RAM memory. So RAM memory and some location. So location should be your address. So address, RAM memory address, and you are writing some data. So let's consider your data which was WR data. Okay, so this is how we can represent. And similarly for the read part, so else if your write enable signal was 0, so you are reading some data from the memory, so you can consider, you can write it down like this. So you can simply write it like this, like RD data is equal to mem sorry RD data is equal to RAM memory of address. So this is how you can implement your RTL design. So I hope everything is clear till now. Like we have discussed all the thing very clearly and very slowly. So I hope this will not bother too much. So we have covered our RTL design part. Now let's jump into the verification. So before verifying our RAM, so see, let's note down the possible test cases. Let's note down the possible test cases of RAM. So see, first of all, your test case should be reset apply and then single write, single read. You have to do single write and single read, and after that, after doing a single write and single read, you have to do back to back write and back to back read to verify our RAM. Back to back write and read. So we are going to test that much amount of test case only right now, and if you want to test more, so you can do, but we are considering that case test only. So right now we are considering that cases only. So let's clear. So let's create a TB. So let module TB and end module. Now let's list. So now let's list down all the signals. So let it take it from here only. Now why we are spending our too much time? So see, here from there we have considered this signal. Now here in place of wire we have to consider range. Here also, see, when you work with the system Verilog na, so it will become more helpful for you because their logic data type was there, which will be replaced by your range and wire, which will replace your range and wire. So it will be more helpful when you are dealing with system Verilog. But right now we are doing in Verilog only, so that's why I'm explaining through RAM. And so right now we are making it through Verilog only, so that's why I am including wire and range. So this is how you can list down all your signal, and then let's connect this signal to the DUT. So just to connect it through the DUT, just copy this signal and let's paste it over here. Now just name it down DUT. Okay, so this is how you can list down your all the signal, and after that let's try to implement a clock. So now first of all our task was to generate a clock. So to generate a clock, let's declare one initial begin block, and here we are, and here first of all we have initializing our clock to 0, and in forever loop so now in forever loop, whenever we are considering a 5 unit of, so now we are considering on time and off time 5 unit, and it's an 50% duty cycle. So forever hashtag 5 clock is equal to negative clock. So this is how you can generate your clock signal. Now we have to make certain task to implement all the test cases. So first of all, let's try to make a reset task. So task reset, okay, and then end task. So we have created a task reset. So inside the task reset, we have to make our reset first of all high. So let's make the reset high. So at that time, your memory block should be 0, or you can say that the address at each location, your data should be 0. Or you can say that at each location, your data should be 0. So that's how you can say that. So we have So we have created a reset signal. So first of all, let's try to make a reset signal to high. So first of all, let's try to make a reset signal to high, and then after some unit of time delay, we are making reset signal to low. So that, see why we have done this part. So whenever you have started your memory verification, so first of all, for before 10 unit of time, your memory reset signal, so before 10 unit of time, your reset signal is high. That means at each memory location, your data should be 0. So that's how we want to achieve this target. So we have done this, and whenever your reset signal is high, so that means you are not getting any write data. So write data will be 0, write enable signal will be 0, and write address signal, or you can say address signal, should be 0. So that's how you can implement this. Now let's consider the another task. Let's consider the task for write. So we have written task write, and in parenthesis we have to consider like address and data, because see, whenever we are passing it through the initial and begin block, so we have to pass its address and data to write inside the memory. So we have consider input, and our data bit is of 4 bit. So let's consider from here only. That's for that purpose only we have declared parameter. So address bit -1 down to 0. Okay, and let's name it down to, let's name it like address 1, and for the another input, and here data bit -1 down to 0, and let's note it down to data. Okay, so this is how we have taken an argument and end a task. Now see, we have to pass this value to the so now see, we have to pass this value to address and data. So address will collect signal, so your address signal will collect value from address 1, and your WR data will collect value from WR data will, so your WR data will collect value from data. So this is how you can implement it. And see, you can pass all your signal at the rising edge of clock. So here we are including @ post edge of clock. So this is how you can make it. And after that post edge of clock, your write enable should be, so after post edge of clock, your write enable should be 1 in your RAM. Okay, so here you are writing something, so your write enable signal is 1 after the rising edge of clock edge, and you are providing some address signal, and along with that you are giving some data signal. And after that, after writing operation, you can make your enable signal to low at the next post edge of clock. So here you have to make your enable signal should be low. So here you have make your enable signal is low, so that read operation or some operation will perform from this. Okay, now similar way we have to create another task for read one. So we have also considered the another task, and this task is for read. So see, in read we don't have to pass data, we have to just pass address, and you can get your data from that address only. So we are passing just address. So we have declared address 1, and in read signal at the positive edge of clock you are providing address 1, and you can remove this data part over there. And after that, so that's only it will take in read. So this much amount of code will require for the read task. So that's how you can implement your design or verification code. Now let's declare one initial begin block, initial begin end, and now from here we are accessing our task. So first of all we are calling our reset task. So we have to call our reset task, and after that we are calling our write task. So see, in write task we are sending some value. So let's suppose our address bit is of 4 bit. So we are sending some address. So 4H, and we have sent 5. And then for data, our data bit is of 8 bit. So we are sending some data. So like our address is of 5, and let's say we are sending data 8-H 34. So this is how we are sending data to for write inside the memory. Now let's consider another write. So see here also we are doing a back to back write, and we are also gonna to do back to back read. So this address should be 6, and we are taking some random data, let's say 78, and then try to read from that memory location. So we are calling the read task, and we are giving the memory location 4H5, and so we are trying to read from the same memory location where we have write. Okay, so this is how we can implement it, and let's try to read from that memory location where we haven't put any data. So suppose here at 4H4 we haven't put any data, so let's see what the data were coming. So I hope I have done all the part and I have written all the code. Now let's simulate this file, and before that let's try to finish, because here we have used clock. So after 100 unit of time delay we are finishing our simulation. So $finish. Okay, so now let include our dump file so that we can able to see our waveform. So let's include it. So initial, begin. So this is how you can also create your test bench, because see, in verification test bench is very important. If you are not able to design RTL, so that's okay, because no one gonna to see your RTL skill, but the verification skill, how you are planning your test case, is very important. So you have to take care of it. Now we have to include dump file. So dump file, $dump file, dump.vcd, and $dump wares. Okay, so this is how we have to create it. Now let's try to simulate this code. First of all, select one tool. So let's select Synopsys and open EPVM. Now let's see. So here you can see the waveform. We are getting at a fourth location, since we are not uploading anything. So we are getting the value 0, and at fifth address location we are getting the read data as 34, and here at sixth memory location we have updated 78. So whenever we are trying to read the data, so we are getting 78 only. So this is how you can implement your RAM. So I hope it is clear to you, and still if you have any doubt you can comment it down.